Okay, great. Yeah.
Can you hear me? Okay. So first of all, I would like to thank the organizers. Very nice conference, and it's really a pleasure to be here. I also knew Fred, and I met him many times at different conferences, different institutes. I just want to say very few words. The last time I met Fred, it was actually here at the program on polyhedral products, which you organized. It was 5 years ago, just before COVID, and Fred was part of that program. So Fred was always very nice, very supportive, very influential, amazing colleague. And once I actually shared an office with him in Bonn, in the Max Planck Institute. And we had a lot of time together. And I saw him working. He was very serious about mathematics, as everybody knows. He worked very intensively. And at that time, I did some topology of configuration spaces and applications to billiards, to convex billiards. And Fred liked that work, and we had many discussions, which was very helpful. So yeah, more or less, that's everything I wanted to say. And I want to start my talk with this. I'll show you again. Oh, sorry. Okay. Okay, you may think that I came to the wrong conference. So I know it is mathematics conference and topology, and my talk will be about topology. But it will be topology which kind of is inspired by robots. So let me ask you a few questions. What is a robot? I mean, all these questions actually are quite difficult questions. How can a robot, autonomous system, decide its motion? It probably people at this audience never thought about this, those kind of questions, but they are very interesting questions, and they require mathematics and topology. This is why I'm presenting it here. So Fred liked configuration spaces, and configuration spaces are, can you hear me? And configuration spaces are not only spaces of distinct particles, but also configuration spaces of bodies which don't touch each other, convex bodies or not convex bodies, like people on the street who walk across and they try to avoid each other. There are various configuration spaces, and in general, configuration space is a space of states of certain system, and in this talk we will see examples of this. So the robot must know its own state. The robot must know the state of the environment. The robot must know how to move from one state to another. And the robot must be able to adjust its behavior to changes in the environment. Actually, all these questions are serious engineering problems. And as far as I know, they are not fully resolved. I mean, this video which I showed to you, I took myself at a robotics conference in London. And you could see that this walking robot was quite fragile. I mean, people walked around him and supported him. So he was not very steady. So in this talk, I will discuss mainly this question number 3, how robot must know how to move from one state to another. So let me show you some more pictures of robots or autonomous systems. So this is quite simple robot which moves on the plane, and there are obstacles which can be stationary or not stationary, moving. So the complications. And this is another system. You can think about this whole collection of drones as one autonomous system. So it can be a point, it can be viewed as a point in some configuration space. And controlling such system is a big problem, and mathematically and topologically. Okay, so I'll consider this situation when the environment is fixed and is fully known to the robot. Okay. Actually, it doesn't mean that this is the end of the story. It's just end of my talk, but it's not end of the story. So, okay, so let's see. So, I mean, this part probably people know about this. It's not a new stuff, but let me just briefly repeat this construction. So if we have a system, it has a space of its states, which is called configuration space. And in robotics, people know this quite well and use it quite well. So X will be path connected topological space, so configuration space of our system. Points of this space represent the states of our system, and motions of our system are represented by continuous curves, gamma maps from interval into the space. Okay, so here we have, okay, so there is this map from a space of paths to the pairs of points, pairs of states, which associates with every path the starting and the ending point. This is very well known. So a motion algorithm or motion planning algorithm for our system is a map which goes from pairs of states to motions. So you start with some pairs of states, which you think as this is the initial state and this is the final state, and you want to produce a motion which starts here and ends here. So this condition means that this is a map to x to the I, such that if you compose it with P, it will be identity. So it means that A is a section of this vibration. So motion algorithm is a section of standard vibration. Okay. So far, so good. Okay. So if we have a system, we want to find motion algorithm, which solves this problem number 3, what's in my list. And this means that we need to find a section. And there is a lemma. Well, in topology, we always speak about continuous sections. But in fact, continuous sections do not exist in general. A continuous section exists if and only if the space is contractible. And this is illustrated by this picture. If we have a convex island where our robot walks from A to B, I mean, there is this continuous section which is just going straight from A to B, but there can be some other continuous sections. This picture illustrates the proof. I will not do the proof, but I'll just say that if we have a deformation of our space, which is homotopy starting from identity map to the constant map to some point x0, then we can make this motion algorithm going from x to y. You first go to x0 and then go to y. Okay, so it's not very efficient, but it's continuous. And there is another corollary here, which is important, actually, corollary, that if we have a system which has a non-contractible configuration space, then any motion algorithm for this system will have discontinuities. So discontinuities means that there will be, or algorithm takes as input pairs A, B, initial final configurations, and discontinuity means that arbitrarily close to A, you can find A prime, and arbitrarily close to B, you can find B prime, such that the algorithm will give totally different answer for this deformed input. Okay, so this now topology actually can give numerical measure of how discontinuous this motion algorithm must be. And this is a function of topology of configuration space. So this is expressed in terms of this invariant, which I call TCX. TC stands for topological complexity of X. And it is defined as a minimal integer, K, such that this total space of possible pairs can be covered by K plus 1 open sets with the properties that over each of these open sets, there is a continuous section. So you cannot have, in general, globally defined continuous section, but you can have it locally defined. And this topological complexity is a minimal number of local domains where local section can be found. This invariant has nice properties. First of all, it is a homotopy invariant. So this brings this invariant into this audience. It's for you. This is a homotopy invariant. And it's 0 if and only if the space is contractible. Okay? You can compute this invariant. Oh, sorry, before that, in a recent, well, relatively recent paper, it was Garcia Calcines, Jose. He found that instead of open covers, you can look at partitions of the space, which is more convenient for people in robotics. You don't need to worry about openness. So it's more convenient to partitions, and you get the same invariant, assuming that the space is in our absolute neighborhood retract. Say again? No conditions.
Michael, could you repeat the question?
Yeah, so the question was, are there any conditions on these sets, right? And the answer is there's no conditions, no closeness, no openness, nothing, just arbitrary partition. So this actually is based on previous work of Srinivasan, who was a PhD student, and she was analyzing category, not topological complexity. For spheres, topological complexity is 1 or 2, depending on if dimension is odd or even. I don't know how, when did I start? 36? 26, okay. So maybe I'll skip this statement that TC of spheres is 1 or 2. I'll just skip it for now. There is cohomological lower bound, which is important for calculations. And maybe I'll say a few words. So if we fix some coefficients, some field of coefficients, F, and I'll denote by cohomology like this. So we have cup product, which is a map from this tensor product to cohomology. And we look at elements of this tensor product which are mapped to 0 by this cup. So these are not trivial tensors which become trivial when you multiply. So examples of such tensors are this one, for example, or this one. They are called zero divisors. So we call them zero divisors. And the theorem says that if there are k, some number, k zero divisors, such that their product is non-zero, then TC is greater than k. So this is very useful for calculations. For example, if you look at spheres, in the case of spheres, this is a zero divisor, and the square of this equals this number, or this cohomology class here. So you see that there is n here, -1 to power n. So if n is odd, this is 0. But if n is even, this is 2. So this shows that when it's even, the TC of the sphere is at least 2 bound, low bound. Upper bound is twice dimension, and for topological groups, TC coincides with the category, because in the case of a group, to go from A to B, you can just go from A divided by B to the unit. So this is an example. Let's say torus is configuration space of the robot arm with n bars. It is a group, and for this, using previous statement, topological complexity of torus is category, which is very well known. It's n dimension. And another example is also important for robotics, is a group of isometries of orientation preserving isometries of the three-dimensional space. Again, TC can be computed using category, and well-known result about category of projective space. For surfaces, complexity is 2 for the sphere and for the torus, and then it gets to 4, and it is 4 for all homogeneous surfaces. For configuration space of n distinct points in RD, the complexity equals approximately 2n. So it is 2n minus 2 or 2n minus 3, and this depends on the parity of the dimension even or odd. And this result is definitely relevant to this situation of many drones, controlling many drones. So this theorem about real projective spaces. So in the case of real projective spaces, complexity equals the smallest dimension, K, such that this real projective space can be immersed into RK. And for this exceptional values of n, it is just dimension. So this was joined with Tabashnikov and Yuzvinsky. And this, using this result, we can see the table of values of topological complexity of different real projective spaces. And well, the only thing I understand here is that when n is a power of 2, then the answer is twice dimension minus 1. So if it is 2, then it is 3. And if it is 4, it is 8. And if it is 8, it is 15. And if it is 15, if it is 16, it is 31. The rest is a mystery. So this table is taken from results about immersion dimension for real projective spaces. I just wanted to also mention a result, a very nice, very interesting result of Jesus Gonzalez and Peter Landweber. They looked at a notion of symmetric topological complexity, which we introduced with Mark Grant earlier. So this symmetric complexity is when you put extra conditions that going from A to B and going from B to A should be inverse to each other. And another condition is that going from A to A should be that just constant map. So it's quite natural conditions. They make variation of this notion, and which is called symmetric topological complexity. And the theorem of Gonzalez and Landweber says that for, let's say, n greater than 15, this symmetric topological complexity of real projective space coincides with embedding dimension, which is the smallest dimension n, such that this projective space embeds into Rn. Okay. Okay, so I switched to second part of my talk. Are there any questions? No? Okay. So my title is Topological Complexity of Random Spaces. So in practice, in many, well, like in the picture which I showed you with this robot walking, I mean, the system has many parameters. Like if I am the robot, I mean, this and this are, they're all different states. So that's every angle is a parameter. Every finger is a parameter. So there are many parameters. So the state of a system depends on many, many different real parameters. And those parameters typically cannot be measured precisely. So there are errors. So when we say about state, we do not exactly know the state, and we can, and the configuration space is large. So it depends on many these parameters which are which have errors. So one approach to this is to say that our configuration space is random. We don't know exactly what it is. It's random. Okay? For mathematicians, it's easy to say, it's random. Okay, we accept this. But what does it mean, random space? Well, there are many instances of random spaces, and actually, I think the most well-known random space is a random graph of Erdős and Rényi and Gilbert. And this model, very well known to everyone, so it has n vertices, and each edge between those vertices is selected at random with some probability p, independently of the other edges. So this is a very nice and simple model of random graphs. And on this model, they built what is called the evolution theory of random graphs, how random graph develops when the probability parameter changes and so on. So another random space, another kind of model producing random, in this case, these are manifolds, is this random configuration spaces of linkages. So let me tell you what it is. It's less known. So what is a linkage? So linkage is the closed chain in R3. And here we have bars which have fixed lengths, but the angles between, so these connections are movable. So the joints are flexible. So this chain may have many different shapes. So we fix parameters. One is fixed length, this is L2 fixed length, and so on. And we look at possible shapes which this n-gon can obtain. So this is our configuration space. So formally, it's given by this formula. So it's called NL. L is this vector of length parameters. We call it the length vector. And the space is the following. So this consists of unit vectors of in R3. So let's say U1 will be a unit vector in direction of the first bar. U2 will be the unit vector in the direction of the second bar, and so on. So it is a collection of unit vectors such that if you make it like this, you will have a closed chain. So this is a condition that you will have a closed chain. And then we quotient this by SO3. So we identify we identify polygons if they can be moved one to another by isometry. So this is actually a genuine space of shapes of such n-gons. Well, I mean, this it can have applications. Actually, in chemistry, in biology, in molecular biology, I mean, this is configuration space of molecules like this in 3 space. And those spaces also appear in statistical shape theory, which was initiated by David Kendall. So these spaces have importance for applications, but we can also look at them as a model of random spaces, which it will be on my next slide. Actually, these spaces sometimes are empty, which we don't like when they are empty spaces. And we can ask, when are they empty? Well, this lemma says that the space is empty if one of the bars is longer than the sum of the other bars. So you cannot close the chain. It's quite obvious, right? If I have, let's say, triangle, then each of the bars must be smaller than the sum of 2 others. Otherwise, the triangle will not be formed from 3 bars. So actually, this condition is necessary and sufficient, and we will assume that it is satisfied. And when the space is not empty, then it is a closed smooth manifold of this dimension. So we see the dimension is approximately twice n, so it goes to infinity when the number of bars go to infinity. Okay, so if this vector L is random, so let's say imagine that we have a long chain, let's say with 100 of bars, like a molecule with 100 of elements. And each parameter is measured and has certain distance, some Li. And this distance, we don't know precisely, but we can think of it as being random. If it is random, then we have a random manifold. Our vector, length vector L, is a random vector distributed in, well, I will come to this in the next slide. So we obtain, for example, if each of this length parameter is distributed on 0, 1 with respect to the Lebesgue measure, independently of the other bound lengths, this gives a measure, this gives a probability measure on this space of these manifolds. So it gives us a field of random manifolds. Well, we did it actually first with Thomas Kapler, and then I did it myself, some paper. So this picture shows that condition that, let's say, if L1 is bigger than the sum of these two, this corresponds to this triangle. If L2 is bigger than L1 plus L3, this corresponds to this triangle, and so on. So, so in general, our length vector lies in a simplex of large dimension, of dimension n-1, when n is the number of bars. And when we remove these corners, we remove the volume which we remove n times this. Each of these triangles has 1/2 to power n-1. So it's a very small volume. It is exponentially small volume. So this goes to 0 when n goes to infinity. So for this picture, you probably don't see it because I cannot draw a simplex of large dimension. Well, for simplex of large dimension, the central area, volume of the central area is nearly 1, nearly the same as the volume of the whole simplex. And this calculation shows it here. And the result says that this topological complexity of this manifold of linkages equals dimension of this manifold, which is twice n-3. Why? Well, this I'm not going to prove anything. I just want to say that this manifold is simply connected and has a symplectic structure. And using this, we can just right away conclude this statement, this theorem. So it's quite easy. Follows from this fact that it is symplectic and simply connected. Symplectic, simply connected manifold. Okay. So, okay. So now I come to this model, another model of random simplicial complexes. So I mentioned random graphs, but these are random simplicial complexes of some dimension. So what is this, what kind of model is it? So we call it medial regime. And I'll explain what it means. So look, I knew that we have time limitation, so I made a state definition like this, which may seem not very clear why, what is the meaning of this formula, but let me tell you what it is. So our space or probability space is the space of all subcomplexes of the simplex on these vertices. So we have a large number of vertices, we take full simplex, and we take all subcomplexes of this simplex. And this is our probability space. And on each of these simplicial complexes, the probability of that it is selected equals this parameter p. We have this fixed parameter p to power the number of faces of this simplicial complex times 1 minus p to the power of the number of external faces, external simplexes. So external simplex is a simplex which doesn't belong to our simplicial complex, but such that the boundary does belong. So the boundary is in our simplicial complex, but this one is not included. So I'll just come back to this formula. So intuitively, you can say that every phase comes with a factor of p, and where every external phase comes with factor 1 minus p. So, I mean, I understand that it may not be very clear what is the origin of this formula, but believe me, this is if you take this formula, this gives a probability measure on this set. So, for example, the total is 1. The sum of probabilities of all subcomplexes equals 1, which it should be. So what do we know with this paper with Lewis Speed? What do we know about those random complexes? Well, we know that they are simply connected, which is already a good thing. They're simply connected. They have vanishing Betti numbers up to this dimension log n. And the total dimension of those complexes is asymptotically log n plus triple log n. Asymptotically, almost surely. This means that the statement is true with probability tending to 1 when n goes to infinity. So main question, let me just ask you. So you see, it is simply connected and Betti numbers vanish up to a certain dimension, up to a very high dimension. And then there is extra, this number is much smaller than this number. So there is some extra where it has cells. So you can say, well, is it true that it is connected up to here? You see, Betti numbers are rational homology. So rational homology vanishes, or real homology. They vanish until this number, but it doesn't mean that it is as connected. So the main question remains, is it true that this random complex in the medial regime is R connected, where R is log n? And the answer to this question is still not known, but we have results which are nearly there. I'll tell you. So there is a combinatorial property which is called R conicity, or conicity, which was introduced by Jonathan Barmak, and it is the following. So we say that simplicial complex K is R conic. So R is an integer. If every subcomplex of this K with at most R vertices is connected in a simplicial cone, or equivalently in the closed star of a vertex. Okay, so R conic means that every simplicial subcomplex with R vertices is connected in a cone. And Barmak proved that 2R plus 2 conicity implies R connectivity, and this cannot be improved. Well, there are examples showing that this is the best possible. I will maybe skip this. Next, there is kind of new variation, some variation of this conicity, which is a weaker version of conicity, which is more has more probabilistic advantages to estimate probabilities that it happens. So this is we call this property QR. So this property QR means that every subcomplex with at most 2r plus 2 vertices and at most that many simplices is contained in a star of a vertex. So here, so this property QR is should be compared to the property of 2r plus 2 conicity, and it is weaker than 2r plus 2 conicity because we require only for subcomplexes with that many simplices to be in the core. And this number is smaller than potential number of simplices in a complex with that many vertices. The number of simplices can be, maximum number can be like this, 2 to power this number minus 1, which is 4 to power r plus 1 minus 1. And here it is 3 to power. Okay, so this, this shows that this is property weaker, potentially weaker than 2r plus 2 conicity. And in fact, it is, maybe I'll skip this. So the theorem says that this weaker property, QR, also implies our connectivity, which is good, which is really good. And also, we know that random simplicial complex in the medial regime has this property with probability tending to 1, where R is this number, log 2 with base 3, which is approximately 0.63. Okay, so you can see that we don't have 1 here, which would be ideal, but maybe it's not true. But we have here this number, which is greater than half, 0.63. And from this result, we obtain the following theorem, so which has 2 parts. The first part says that if X is a random simplicial complex in the medial regime, then the topological complexity is at most 2. At most 2. And moreover, there exists a subset of integers of density 1, such that for n in this subset, and n goes to infinity, the set of complexes having Tc equals 1 tends to equals 2 tends to 1. Well, what does it mean, density 1? Density 1 means that if I take n, arbitrary n, and look how many elements of the set are until n, and the ratio, this limit is 1. Okay, density 1 means that essentially you have everything is there. So I want to explain, want to get back to this. I want to explain why do we need this subset? Why do we need this subset of integers? And so first of all, I want to say that this is a work in progress and it's not final. And maybe there will be some other method which will prove this second part of the statement without restricting to the subset. But at the moment, if you look at this Euler characteristic of this random complex, it is a function of n. And as function of n, it is oscillating function. So it goes to, it becomes positive and then negative and then positive and negative. And there are big intervals on each. It has constant sign. And these intervals, the length of those intervals is like 2 to the power 2 to the n, 2 to the n, very large numbers, very long intervals. But it changes sign. And when it changes sign, we cannot exclude possibilities that the spaces are contractible or have TC equals 1. There is a theorem which I wanted to mention. There is a theorem by Mark Grant and Greg Lupton and John O'Prea, saying that TC equals 1 only for spaces homotopy equivalent to odd dimensional spheres. So this should be very easy. If you show that, let's say, some Betti number is 2 or higher than 2, it should be, it's done. It implies that TC cannot be 1. But again, there are the situations when the Euler characteristic changes sign, and there are some questions. Any questions here? No, okay. So, this last part of my talk will be about random complexes on infinite number of vertices. So what? So before, until now, I looked at random complexes with finite set of vertices, and we asked what happens when n goes to infinity. Okay. So now I take n equals to infinity. I look at the limit. Okay. Can we look at random complex with countable set of vertices? Yes, we can. Before that, let me mention that the situation with graphs. Erdős and Rényi looked at also to the case of infinite graphs. And they showed that if we take infinite set of vertices and we take probability, edge probability 1/2, so each edge is chosen with probability 1/2, then the resulting graph, infinite graph, is unique up to isomorphism. And it's called radograph. Or sometimes it's called random graph. So what is amazing that this graph is unique. This probability 1, the resulting graph is this R, what is called radograph. And this radograph has amazing properties. One of those properties is that if you take any finite number of vertices and edges and remove from this graph, what remains is the same graph. So it's, if you want to have a, let's say, network, electrical network, such that it is very reliable, I mean, if you put a radograph there, and this any finite number of cuts and some kind of problems in this network, it will work anyway. So it's an amazing graph, this radograph. And actually, there is a survey paper of Peter Cameron, which is very nice about this graph. And this graph has a property. I'm okay. A few more minutes. Huh? Okay. So this graph has a property, the following important property, which characterizes this graph. That if you take any finite number of vertices u1, un, and any finite number of vertices v1, vm, then you can always find in this graph another vertex z such that it is connected to all u's and it is not connected to any of the V's. So this is called, I don't know, characteristic property of the random graph. Okay, so now we want to introduce a rado-simplicial complex. So there is also a few more minutes, yeah? Doesn't like it. I can stop anytime. I can stop. Okay, summarize. Okay, so let me summarize it quickly. That there is a notion of rado-simplicial complex, which has certain properties, which I will skip what is the property, and there is a characteristic property which generalizes that one for rado graph, and what is summarizing. So okay, so now we take a random complex, so we can introduce probability measure on the set of all. So we take delta n, simplex spanned by natural numbers, so it has countably many vertices, and we look at omega is a set of simplicial complexes, subcomplexes of delta n. There is a natural probability measure on this of the space of subcomplexes, and the set of R, the set of complexes which are isomorphic to each other and are rado complexes. It is measurable and it has full measure. And also what is interesting that it's this part, that geometric realization, the geometric realization of the rado complex is homeomorphic to the simplex of dimension, infinite dimension. So topological complexity is 0. So so what I wanted to say is that it may not be accidental that there are these areas when Euler characteristic is close to 0, and maybe there are some values of n going to infinity where topological complexity of random simplicial finite random simplicial complex is 0 or 1. And it can be related to this fact that in the limit, it is contractible. It is, we know it is contractible with probability 1. So, okay, so thank you for listening. So wait a second. I just want to show you again this picture. And I want to tell you that, look, imagine that you are crossing the street. Here, let's say there's, when you come to the institute, many big crossings. And when it's a sign you can walk, you walk on the street and you see many people going opposite, and you try to avoid people walking against you. So this is a situation when you, let's say, if you can think of yourself as an autonomous system, you walk in an environment which is changing, which is moving, which is, so this situation is not covered by what I told you. Because in this case, the environment is changing while you are moving. Imagine that this is a robot, and he should see that people coming against him, and he should understand what they want to do and what he wants to do. So just to finishing, Steve was very generous. Thank you. I just want to give this 2 references of approach where we take into account environment and changing of environment. So it's a different story, but it also involves configuration spaces and vibrations of configuration spaces. So thank you. Thanks very much.
Yeah. Okay.